Okay, so from here we're going to take a look at working through some of the problems that are given to you in your notes that are listed, or a file for those is on the web page for the class. This first example, we're looking at writing symbolic notation for an isotope. So theoretically, I give you a list of isotopes of particular elements and ask you for the notation, complete notation that goes with them. So we're just trying to find a different way to represent uranium-238 in this example. So before you do this, you'd want to have read through the materials. First, know what an isotope is. It's an atom of an element that has a different number of neutrons than another atom of that same element. So, uranium can have many different isotopes of uranium. So in other words, it has the same number of protons, same identity, but it has different number of neutrons, which makes it have a different mass, or mass number. So this 238 is the mass number of this particular isotope of uranium. And your mass number, looking at your book and other things like that, you would find that the mass number is equal to the number of protons, which are positively charged, plus the number of neutrons, which are neutral. You might also see that written mass number referred to as A, protons or atomic number, that's always the same thing. Atomic number is always the number of protons, which you might see that written as a Z number. So that's a Z, and of course plus the number of neutrons. So this problem here, we're going to look at this one. We would want to have a periodic table to go with this so that we could locate this number of protons, or the atomic number of these things. So uranium-238, I'm going to just quickly go to my periodic table, and then I'll pull one up. Here's uranium. So this is its atomic number. That's its symbol, and this is a weighted average atomic mass. So that's a weighted average of all of the isotopes of uranium. But here's its atomic number, 92. So that means that all uranium atoms have 92 protons. So regardless of which isotope it is, which mass number it is, the protons, or the atomic number, is always that. So when we're looking at this, we're solving these kind of problems, we're trying to get the total understanding of what's in the nucleus of a particular atom based on the mass number. So when we go back through here, we'll look at this, and so we'll start out with, well, we'll just write the symbol for the element uranium, which is just U, capital U. This mass number, 238, symbolically you would write it right up here, kind of a superscript and to the left of the symbol. So this is uranium-238. So if you see this notation, you're going to call that uranium-238 also, just like you're reading it out right here. And then we can place that atomic number, 92, at the bottom as a subscript kind of number right there. And this will give us our notation for the uranium-238 isotope. You also could say, oh, if the mass number is 238, and we measure these, one of the units we use to measure that are atomic mass units. Well, that's going to be equal to the number of protons, which is always 92. So 92 protons. Each proton is basically a one atomic mass unit, and so is a neutron. So if we wanted to, say, solve this kind of problem and determine how many neutrons are in a nucleus with these 92 protons for this particular isotope of uranium-238, we could just subtract 92 from both sides and solve for the number of neutrons. So if a question said how many neutrons are there in the nucleus, you could say 146. So there are 146 neutrons along with the 92 protons, and that's what makes this add up to 238 atomic mass units. then I could tell you, well, write the symbolic notation for each of the following ions. So I could give you a list of information from which you would have to discern or determine the number of, or write the notation for based on the number of protons, or its atomic number maybe, the mass number, and the fact that it has a charge. So the difference between an ion and an isotope, we already said that an isotope had different numbers of neutrons. So this is when you have an element when it has lost or gained electrons to form an ion. So something with a positive charge is going to have lost negative charges. So this element right here has a +1 charge. That means it has one more proton than it does electrons. So if you're looking at this atomic number 55, well, that tells you how many protons there are automatically. So 55 is the atomic number, 55 is the protons. And so that'll tell you that it has that, and you could locate it on the periodic table. So I'll pull up the periodic table again, and we'll just move this around, and we'll go up here to the element with 55 protons. So that's xenon. So I'm just going to go right to the next one, and if you look at that on the other side of the periodic table, and I don't know if my screen is picking this up or not, but it's cesium. Cesium has 55 protons. Its atomic number is 55. Its symbol is capital C, lowercase s. So right away I can see there's a symbol, CS. And then I know that its mass number is 133 atomic mass units. 55 is its number of protons, or its atomic number. And it has a charge of +1. So if we have a charge on an atom, which makes it an ion, then we put that charge to the right of the symbol superscript up here. So this would tell me that it's an ion, that if you look at that, it looks like this would, when you look at the number of electrons it has one less electron than it does protons. So this has 55 protons, and it has 54 electrons. And if you want to calculate the number of neutrons, you just can take your mass number, take away your atomic number there. So when you subtract that, this will become 7, 8 neutrons. So that's how you get its nuclear makeup. So these two things are in a nucleus. These 54 electrons are in the electron cloud. So when I was scrolling through my periodic table a second ago, I almost went ahead to the next part. These 54 electrons make it what we call isoelectronic with xenon. So a second ago I was scrolling across through here, kind of anticipating where I was going to be going with this. Right here I put the wrong symbol in there. I need to fix that. XE is xenon symbol. I put XN, I think, but I can fix that really quickly. But it means that it looks electrically like has a charge. Yeah, I did. But this particular electron configuration is like that of xenon, which is a noble gas, which are more stable than cesium is by itself. So when cesium loses that electron, it becomes more like a noble gas, has the same electron configuration as a noble gas. which is beneficial because it helps stabilize the cesium atom as it becomes a cesium ion. And that usually happens. This process of losing electrons. So if you lose electrons, we call that oxidation. And that electron went somewhere else, probably to, in most cases, a non-metal or a non-metal element will gain that electron. So these losing electrons to become oxidized, or oxidation process, results in what we call cations. Cations are just positively charged ions. In order for that to happen, we have to have the other part of that, I guess you'd say, gaining electrons. When that happens, the substance that gains electrons, we call that process of gaining electrons, we call that reduction, by the way. And reduction produces anions. Anions are negative. So this kind of, understanding that terminology that you're coming across as you read through your book. So losing electrons is oxidation. So this cesium atom was oxidized. It lost its one electron, and it still has its 55 protons in its nucleus, but it only has 54 electrons now. But that's okay because it looks like xenon as far as electrons go. And which, so this is kind of a process of stabilizing the cesium atom for it to become an ion. So then sometimes you might come across a problem where this one says this ion has 24 electrons, 30 neutrons, and a +3 charge. And I might be asking for, the notation for that. So, I might be like, what does the notation look like? So you have to kind of do a little Sherlock Holmes right here. 24 electrons, 30 neutrons, and a +3 charge. So this +3 charge means it has 3 more pluses than minuses. So 3 more protons than electrons. Okay, so this will kind of give you a clue now. So if it has a +3, there are 3 more protons than there are electrons. So 3 more protons than there are electrons. So if you know you've got 24 electrons, then you had 3 more protons than that. This element has 27 protons. So also it has 30 neutrons, which also are important because we have to write notation. So if I go to my periodic table, I'm looking for the element with 27 protons. There it is, cobalt. So this is our symbol, capital C, little o, and we can just verify that the number of protons or the atomic number is 27. So from here, I can say, okay, I know that this is cobalt. I know its atomic number is 27. I know it has a +3 charge. Now I can find out what its mass number is by calculating a sum of the protons and neutrons, because mass number is the sum of the protons and the neutrons. So this is 30 plus 27. This is mass number 57. So our isotope notation for this particular isotope of cobalt that became an ion, it lost 3 electrons. So this is our cobalt ion. Its mass number is 57 in this particular case. Another way, since cobalt has more than one possible oxidation number, we also would identify that as cobalt 3. So this is a cobalt 3 cation, because cations are positive. So we'll talk more about those possible oxidation numbers and stuff later. It's just because it lost 3 electrons. Sometimes cobalt, being in that transition metal group, can lose a different number of electrons than 3, and you have a different charge on your cobalt ion. But it's still cobalt. The protons stay the same. If you change the number of protons, well, you have a different element. So that's what happens in like nuclear decay. So if you have a isotope of an element whose nucleus is not stable, the protons and neutrons are not in a favorable enough ratio, it will break apart. So and form a new element, because it could lose some protons, or it could a neutron could become a proton, all kinds of different things like that. But this will get you like the notation for this kind of problem to help you solve it.